All right, folks, welcome to the class. We're getting there. I guess what we'll be doing is finishing the register allocation topic, and then I wanted to discuss one of the important application of register allocation to a particular type of peculiar type of register architecture, which prompts machine-specific optimization. So we'll first go through this, and then we'll take a look at the register architecture for a particular reason. It allows you to share registers across threads. So as you know, it's a very unusual type of architecture. And these were the slides we are looking at. I'm going to actually put those on the class Canvas web page, but of course you'll see the relevant parts in the part of the recording here. So what we had covered was what exactly is a live range and what exactly is an interference graph, and the live range tells us what is the it's a range which has endpoints. It starts with definitions of the values, like in this case in a basic block it's single definition, but across basic blocks there could be multiple definitions which could in different basic blocks which could start the definition variables, and then it reaches the uses as you're seeing here, going through the uses, and then there is a last use at which these definitions get used. So the interval of all the points between the definition and the last use point is a live range. And here it is, of course, just a single basic block, but in general you can imagine that this would be across multiple basic blocks. And we had also seen the concept of webs, which means that these live ranges which are across different basic blocks should be considered together for register allocation. We had seen that last time, and then we'll revisit it a little bit. And once you determine these live ranges, we haven't seen how to determine these live ranges across basic blocks. That's what we'll see today. We decide that these, after we determine them, we determine the corresponding webs, and then we see if they interfere. They are concurrently present at a given program point. And if a live range of one variable passes through the definition point of another one, then they are said to interfere. And if they interfere, obviously, the first live range may be holding a particular value in a given register, and that register cannot be given to the second live range, whose definition is it's passing through, because obviously it will override that value, and therefore it cannot be in the same register. And so this interference is captured, that the two cannot share a register. This relationship is captured by this interference graph, as you see here. And then the next thing that we see was how to color this in a legal manner. That means if two nodes are sharing an edge, they cannot have the same color. So under this constraint, we want to fit this graph or color this graph with the available number of registers. Coloring means giving a register to that particular live range. And in this case, you can see that we need at least 3 colors. We can, of course, share the colors across 2 nodes which do not have an edge amongst them. The moment you have an edge between 2 nodes, they have to have different colors. So under these, you can see that 3 colors are really essential here. And using those, we can, however, color the this particular live ranges and put everything in the register. Now, if you have less number of registers, which is typically the case, the number of ranges which interfere is typically much higher than the number of registers. The number of registers is typically either 32 or maximum 64. There are two kinds. One is floating point, one is integer, and they hold the values, and they typically are no more than 32 or 64, and we have lots and lots of ranges. So that leads us to the problem of which one to really not keep in register, which is called as a spilling problem. And the way we will do this solve this particular problem is by using this kind of an algorithm. First, we'll do the live range analysis, which is what we are going to look at, and from there how to come up with the corresponding webs, which are combining live ranges, which share the uses or the definitions. So that's the first step. The next thing is to find out if they interfere and build the interference graph. The third thing is with each web, we want to compute what is called as a spill cost. What is exactly a spill cost? The spill cost tells us that in a given range, how many definitions and uses participate. And if we don't keep this particular range in a register, then all those definitions have to have a store associated with them. And uses, of course, every time we need a value, it's not in the register. So where do we get it from? From the memory. And so that costs us a load. Now, if some of these definitions and uses are also inside loops, they obviously execute much more times in terms of number of executions of these. And so they're appropriately weighed. If they're inside a loop, they're given more weightage. If they're in a linear code, not out inside a loop, given lesser weightage. If they're in a doubly nested loop, they are given even more weightage, which is 10 to the power 2 typically. 10 is an arbitrary number of weightage that is given if they're in a loop. And it's a static analysis, so we don't know exactly the frequency of execution of a loop. So we just weigh them more than the ones which are in the outside of the loop. So if there is some live range which is going through a deeply nested loop, maybe 3 or 4 levels of nesting, it will be given a very heavy weightage, 10 to the power d, if there is a d is the depth of nesting. And it will be considered to have a lot of spill cost range, which is not really going through a deeply nested loop like this, but it's not even go through a loop. So it will be given less weightage, and so it will have a less spill cost. So what does spill cost tell us? Spill cost tells us the penalty of not keeping the value in a register. And when we are faced with a problem, should we keep A in a register or should we keep B in a register? Because I got only one register to fit either A or B. So the one which will fit will be the one which has higher penalty or higher spill cost. The one with the lesser penalty, we can live with some of the load stores, but imagine one of them has a penalty of 1,000, second has only a penalty of 70. The one which we can live with is 70. So the higher the spill cost is, will be the candidate for register allocation. Will be given a register over the one which has a lesser spill cost. And that is what will be done by what with that graph coloring algorithm, which we saw a little bit of a illustration on that. We'll also look at the details of algorithm, which is called as graph coloring algorithm for register allocation, which does this user spill cost and all these things and makes a decision of which web gets a register and which one doesn't. And then after that, the register assignment is done. Typically, most registers are interchangeable. In other words, they all interoperate with different instructions. So that is what is called as an orthogonal register format, which basically means that in order to do multiplication, it is not that you have to worry about only a subset of registers. And in order to do maybe division, you need to have yet another subset. So this kind of situation is not there. Any register operates with any instruction, of course, of the right kind. Integer registers operate with the integer instructions, and the float ones obviously will operate with the float ones, things like that. But it's not that a specific subset of registers is accessible to certain instruction in the regular processors. So that's why it is not a machine-dependent optimization. It's a machine-independent optimization. But in some processors, because the way they are constructed, internal data paths and so on, only certain registers are able to work with certain instructions. And because of that reason, this coloring pass, or which instruction gets what, will become complicated. It is not simply based on the spill cost. It is based on which register is needed where. So that will be machine-dependent optimization. We will not get into that for now, and we'll look at the the other specific kind of machine-dependent optimization as a beginning for multi-threaded processors. Okay, so in our current allocation algorithm, we'll just give a color, whichever is available, to the value, and therefore all the values or registers are able to interoperate with the underlying instructions. Once we are done the register allocation, we know that some instructions will have register allocated to it. Others will not get the registers because they had to work with the there was no register available, they were spilled, and they had to get those loads and things from the memory and so on. So we'll generate the necessary load stores for those instructions or those values which did not get registers. And then we'll generate the code, of course, for the rest of the IR, for which we need them to be in a register, register moves, addition, subtraction, etc. And wherever we are not, we'll use scratchpad registers to load and store them, and then have those operate through the scratchpad registers. So what are two kinds of registers that typically we have? We have persistent registers which are allocated. So for example, A is given a register at its definition, and it's still its last use, it persists with A. That's called as persistent register. A is held in a register. And that's the goal of register allocation, to decide on these persistent registers to be allocated to the values. But of course, we also need register to do temporary computation. So whichever is spilled value, let's say, because of registers not being available, whatever. Now that spilled value has to be brought in. It's not only to be brought in from the memory interface unit, but we have to operate on it. And so for doing this operation, we'll use some set of registers which are just kept aside for that, which are called as scratchpad. So they won't hold any permanent values, but they will temporarily get a value. You will carry out some manipulation on that value, generate some result out of it, and then store that result back. And again, those registers can be used for something else, for the next calculation, etc., which involves some spilled variables. So those are scratchpad registers, and using the scratchpad registers and actual registers, the code generator will generate the final code, which will have spill code, which is like load stores, bringing the values in, etc. Also will have these scratchpad registers and will be used for generating the instructions there. And of course, wherever we have registers allocated and those values are held in those, the instructions will directly take those values out of those registers. Let's say A was given a register 7. Wherever we have operations on A, we'll use register 7 so that it is maintained current with the values which it needs. And second important thing is if you have a register which is a scratch pad, then obviously you will just use that. And the values which are in the persistent registers are not to be disturbed through the live range. So they will not be overwritten. So the code generator will take care of those issues. So this is how the overall register allocation and code generation framework works. Now, as part of this, two parts we had to see here is one is how does this do it for live range analysis? How do we actually find these live ranges across basic blocks? That's one thing. How do we form the webs? Number two. And the third is the coloring algorithm. So those are the three important things. So let's shift gears and before we get into the coloring, we will try to do the generation of the live ranges and formation of webs. So let me switch gears here, and we'll open another. Okay, can you see my presentation on the live variable analysis?
Yes, yes, yeah.
Okay. So let's define liveness first. So liveness is some value has been computed, the definition of that variable earlier, and it is flowing through the data flow graph or control flow graph. And periodically it is being used at different program points without being overwritten again. So this particular thing is called as a variable is live during this particular interval. And we want to find out whether a variable is live at a given program point or not. And how do we find that out? So let's use the definition of the liveness first. We call some variable live at a given program point, provided there is a use of that variable somewhere downhill from the current program point. So if somebody is going to use that variable at least along one of the paths from which starts from the current point downhill, going forward, that means with the control flow graph, if somebody is going to use it, then we call that variable live at the current point. So just one use is sufficient to call it live. And if nobody is using it, then it is called as dead. Using this particular definition, let's see if we can find some sets here, just like other data flow analyses do. So if we want to find out what are the variables which are live at the entrance of the block, and if we are to find what are the variables which are live at the block, and want to do it even in between, then we have these respective sets defined just like any other data flow problem. So all the variables which are live at the beginning That means at the entrance of the block, if we go down from this entrance somewhere along the way, we must find some use of that variable, and that means that's the only way it will be live. If there was no use from going from the entrance down through the basic block, maybe its successors, etc. If there was no such use of that variable or a value, then the variable is dead. Similar is the definition about what is live at the end of the basic block. If from that point onward there was no use, it's dead, otherwise it's live. And what we want to find out is the liveness as it affected by an instruction or by a basic block sits that in between. And we want to also find out what is the relationship of something which is live at the exit of the block to the one which is live at the entrance of successors of the block. Now, one of the big differences in the analysis is that, as you might have seen or imagined, this is a backward analysis, unlike forward analysis is in data flow. I hope you are still remembering the backward versus forward. What is a backward analysis? That means liveness at a given point is decided by what is going on downhill from that point. If that is the case, then we had to decide if something is live at a point based on what might be going on downstream. So we first record what is going on downstream and then move backwards and then assert on the liveness at the given program point. If that is the case, if you're using the information from downstream to make decisions upstream, that is basically going against the stream. That is called as liveness. But many problems do the reverse. They will use the current information to decide what to be done downhill, and those are forward problems. So liveness, then very busy expression, anticipatability, all these are backward problems. So how do we do this? So let us look at some examples. Some means we have determined variable x and z were live on the left hand side, which is out of I. So at the end of this instruction, if we determine that x and z were live, what happens when we move back through this instruction? That's the question. So you can see that the variable which is really unaffected here is z. So because if z was being used from the out downhill, and z was also used in the instruction here, although that is not really necessary. When you look at the usage of z downhill from the in point, in of I, it will be answered yes, that yes, z is going to be used somewhere downhill from here before it gets overwritten or before the definition occurs. So that answer, if it is yes at out of I, it will remain yes at in of I, and z will remain live. Now let's say y was not live at the out of I, as you can see here. So there was no use of y from this point downhill. But now if you ask the same question at the entrance, the answer becomes yes, because in between you have run into a use of y. And that's how the answer to that question, whether y is live, becomes yes. So whenever if something is not live downhill, but if in the current basic block suddenly there is a use of that variable, then it will become live. Now the reverse case, x was live, so x had some variable use from this point downhill, but in terms of whether it is live at the beginning, we'll ask the same question. And the answer to that will be, hey, I'm looking at a different value of x here, before this definition x point. And as far as that value of x is concerned, it is not being used before it's being rewritten, which is coming at the top. And that's why this x value will not be considered live at the entrance. So similarly, you can see all the other examples. Something remains live because it's unaffected going through the block. Something was not live becomes live because it was used in that instruction. And something was live, but we ran into its definition point, so that live range has terminated there. So when we go up like X here, it no longer is live. Now, we are not working in this particular case in a SSA type of a framework, otherwise it will become very clear that in the last example, although X is live in both cases, in and out sets, there are really two different values of X. The value which is coming from top is a different value. Let's call it X0, and that is used on the right hand side of X is equal to X plus 1. But the value which is generated on the left hand side is a different one, which is called in SSA format X1. So if you really look at it in that way, X0 is live at the inside and X1 is live at the outside. And we usually don't SSA in terms of liveness analysis, but if you were to work, that will be what will be caught there as two separate values. And in general, although we don't designate those as SSA, you will see that first value X0 could be given a register and it's independent of the second value. Second value X1 may or may not be given register, or vice versa. X1 could be given and not be given. And so that way they are decoupled. They are not the same value. So general rules for computing liveness is based on the uses and definitions. And of course, we can write these kinds of equations based on the uses and definitions of the variables in a given basic block, and are able to write the data flow equations. If something was live and if this was not redefined, then it will remain live. And these kind of things could be easily caught by writing a data flow equation. That's like what we did. One of the things is equations which propagates liveness through the basic blocks is very simple. So if something is live at the end of the basic block, which is given by the outset of the basic block, and there is no definition of that value inside the basic block, then it remains live. And this is the fact which is shown by this first expression. So if something was live, out was true for that variable, and there was no redefinition of that X within the current basic block, so it will remain live. If there was a definition of X, that will not remain live. That will be taken out by subtracting the def set. On the other hand, regardless of whatever was live, downhill or whatever, if we are looking at the uses, the moment there is a use of a particular value in a basic block, you will see that it will become live at the entrance at the inset, because if you look at it from that standpoint, there is a use from here of the current value without going through the definition, and that use is found straight in the same basic block. So these are the liveness expressions between different program points, and they also become relevant and applicable at the basic block level. It is equal to out minus def union use. And although here they are shown as between instructions, one could easily compute them by using the definitions and uses the way we have defined them. So now one of the things is how do we decide the control flow effects of liveness? So those are also computed in the backward sense, and very easy to see it. For example, if X and Z were to be live at the entrance of B1, what it means is there is a use of x or of z through B1 or down from B1 rather, more precisely. It need not be exactly in B1, but maybe in some path which starts at B1. And similar is case with x and y. Now if we were to ask the question that, so what are the variables which are live at B? You can easily see that the set of such variables will be maybe some coming from B1 and some others coming from B2 or whatever the second branch. So in short, x and z were live in B1, x and y are live in B1, Bn, and therefore at B's exit, it could either be x, y, or z, and all three of them are declared live. So the general rule is go backwards, take a union of the insets and propagate it backwards to the outset of the predecessor. And in terms of computing the liveness of the variables, again, a variable is live if it is live along at least one path, and that is reflected in one of the insets. And therefore, to decide the set of all variables which are live, we'll take unions of all the insets. So here is the second equation out of B. Now you can see this is also backward, is equal to B dash, which is a successor of B. And we'll take this insets and calculate the outset. And once we have these sets of equation for computing the outset from the insets of successors, then propagating it backward towards in the inset of the first variable and so on, you can transitively achieve propagating all things which are live through all the basic blocks, just like reaching definitions and all, same analysis in an iterative way, except in a backward sense. And once we propagate this information and stabilize the Newton, the liveness is therefore known everywhere by using iterative algorithm. So here are again two core equations. One is to propagate backward across basic blocks. What we do is we just simply take a union of all the insets of the successor, which reflect what is live in each successor. And if it is live in a given successor, it must be live at the end of current basic block. So that's why union. To propagate them further towards my own union in terms of the basic block that I'm operating on currently, all the live ones survive if they are not redefined. So that is basically out minus def. And then in addition, some which might be defined within that block get added, which is the use. This is a system of equations. It's again seeded and manipulated and rugged in the iteration ways is propagated, and even if the loops and all are encountered, we'll go through all this and propagate them backwards, and once they stabilize, just like in this particular equation, they will converge. How do we seed this analysis? You can see that the seed of this analysis could be that whatever is live and is upward exposed in a given basic block is included. It's in its inset because its use is seen from the top of the basic block, so that becomes live at the entrance. So insets are initialized to the upward exposed uses, and then we keep propagating and converge. So here is that example which you can work it out offline, but it does this kind of calculations and propagation of these values starting with the uses in a basic upward exposed uses in a basic block, initializing the insets, computing the outsets of the predecessors, using them, using the union, and then again propagating it back to their own insets and iterating few times until conversion. So I'm not going to show the details of this, but you can check it. So again, this is a backward flow analysis framework which computes these kind of um, information about the which is live where in terms of the variable names. And from here, we want to be able to find the webs. I think I had kind of mentioned that, but I will quickly revisit, and then we'll get into the interference graph and its coloring. So before do the webs and interference, are there any questions about live range computation? It's a fairly straightforward algorithm. We do this in our undergraduate class because the modern machine, they're all register-oriented architectures, which basically means that you cannot do any operation when the operand is in memory. The operand must be brought into a register before we allocate, before we can operate on it, which is the design principle of RISC type of machines. And that basically mandates that you got to keep the most of the program values in the which is what is the reason why we had to do this register allocation for any kind of RISC backends and get these values or generate these values in registers and then keep them throughout their live range in a register and use them out of registers, saving on your latency and many other things. So that's any questions about live range? Okay.
Nothing on chat, yeah.
Yeah, so looks to me, I think this is a fairly straightforward topic once you have done the data flow. Now let's, before we get into the, I'll just quickly one more time revisit the concept of webs and then we'll do the interference graph. So we kind of looked at it last time, so it will be fairly brief, but I will mainly tell you the algorithms which are really important in computing the web from the, because that's where some depth is there. So what it really is a web, as you know, is these are our basic blocks. And webs tell us that this is my definition V1 of a variable. This is my another definition. It's the same variable V, which is being defined. So I'm kind of doing it in a SSA way. This is the use of V. So you can see that these two definitions, V's, this is really V here, and this is also V. These generate these values of V, and then they feed it to this guy. So this, the question is, and let's say this is my last use, and this is my definition point. So using that, this is my live range here, and this is my live range here, from last use to the definition point. How do we find that? And everything in between, on all paths between these two is the live range. That's basically how it is defined. Because the value could go from here and go along one path and then reach this, go on another path and reach this, go along third paths and reach this. So all these paths which are there between these two endpoints is basically the live range. So first of all, how do we determine it? That's one question. And then once we determine it, how do we generate these webs from it? So you can see that what we need to worry about here is the endpoints, which are really important. So this is my last use. And after I do my liveness analysis, I want to find out that basic block wherein the value was live here at the beginning of it, but at the end of it, the value was not live. That tells somewhere during that basic block, the value had its last use. And so I look for this kind of differential information. It must be live in the in. This is my inset. It was live here, and it was not, of course, live in the outset. And if that is the case, then I know that somewhere in that basic block, the last use of that value was there. And that's how then I scan the block and I locate the last use point of this V, and that's my one of the endpoints. Now, if you look at the definition side, however, exact reverse is true. So the value is not live in the beginning or in inset. I won't find that variable. But the value will be live in the end of the basic block. I'll find it in the outset. So exact opposite. So again, I look for this type of difference when the value was not beginning but live in the outset. And again, I scan through this and locate the definition point, which is this. So that's how I find the endpoints of each value. And same thing, you can see that it will be true here as well for this definition point, not being live in the beginning, but being live in the end. So that's how I get these endpoints of use and definitions. And then I start with the block which contain the last use. And just like we saw in a loop enumeration algorithm, we will scan backwards along all the basic blocks and their predecessors and so on, unless and until we reach this particular and all these blocks which I will enumerate going backwards from the last use towards the definition, all the paths that I will plan toward that particular going to the definition, they will be included and they will constitute my live range. So that's how I really develop the live range. Now, after having done that, what I simply look for is, are there two live ranges intersecting in some block in terms of their use? And if the answer to that is I had this whole interval which is modeled in terms of different basic blocks and list of variables over here or statements or IR statements if the block is partial. That's how the live range will be described, and I take their intersection and they have some common use in that. If they have, then I will merge them, okay, for a given variable, of course, given value. And if they share also a definition, I'll still merge them. And so you can see here that these two will get merged, and that will become a web. That part I think we had looked at. So web must share a common use or a common definition. And once we determine these live ranges, we can take their intersection for a given variable. The intersection is null, then obviously it is not a web. There are two different live ranges in that case, or two different webs. But if they do have an intersection, that means they share a common use, and that becomes a case of common web here. They must share a use or a definition. Okay, so we keep combining them and generate the webs. And now let's go back to our interference graph and the coloring side of it. That way we'll be looking at this now, what happens afterwards once we do this webs business. So let's go back to this overall algorithm which we had looked at. We looked at how to determine live ranges, then how to determine the webs from there, and then the webs must also interference in the definition point of a one web. The other web should cross through that, and if that happens, then they are interfering, and then we'll put an edge between them, and once we build the interference graph, then the next question is how to determine the register allocation. So before that, of course, we need to worry about generation of the spill cost, and let us look at the spill cost generation, and then we'll look at coloring and so ideal spill cost is if we really knew how many times each loop executed, each instruction executed, so that we can count the dynamic number of load stores for each web, it will be the best thing, but we can't do that. Even in a profile guided approach, it will be, the profile will show that, okay, this happened during one of the executions, but what can we say about the next one? We cannot. So what we do is we do a static approximation, because finally we just have to kind of weigh whether given web should be kept in a register over the other web. It's a relative decision based on whether one is really going through a loop or whether the other one is simply a linear set of instructions. So what we do is we want to, of course, give higher priority to which go through process in the loops. So we assume that maybe each of the loops executes 8 or 10 times, and this is how we compute the spill cost. We sum all the depth sites, and that's a cost of store, which will be there if we did not put this in the memory. And then we find out what is surrounded loop nest for this particular depths. And then we raise them by the depth of loop nest, D, because that's how many times potentially this could execute. If each loop were to execute 10 times, if it's D deep depth, then it's basically D to the power 10 to the power D. Similarly, we also look at all the use sites, loads instructions, and then again weigh them 10 to the D. And we sum them, all these loads and stores for each web. And our goal will be, so this is how statically we'll determine the spill cost for each of the web. And the interference graph that we have carries that information. It carries the name of the web, and it also carries the spill cost for that particular web. So if we don't give the web a register, then obviously roughly this will be the cost we'll have to pay because of the underlying memory accesses for load stores. So that's the idea here. So this is how we'll determine it, and we'll decorate the so once we have the interference graph, we'll find the spill cost and we'll decorate the interference graph. So now let's go back and see, once we have the interference graph, how do we color it? And that's the last step that we are going to look at here. So obviously, interference graph is very big because we have so many webs which participate, which interfere with each other, and there are so many live ranges and so on. And the core principle, of course, that we are following here is that if they interfere, they cannot share a register, or they cannot be put into the same register, because that will create some illegal program. So if they have an edge, they must be given different colors. And this problem is NP complete, as you can imagine, because of the complexity. The compilers could have chosen, and this is where the most interesting part of decision making took place in the compilers area. The compilers would have said, okay, yeah, this looks like a very hard problem, but let's algorithms and theory people are extremely smart, and of course I have fully respect for them, and they keep developing all these more and more interesting algorithms, approximation and this and that. And as they come across those, let's incorporate those, which might cost a little bit of compilation time, but which will give you a great solution. That could have been the direction of trying to, use better and better algorithms for solving the problem. But that's not what they did. And by looking at the problem very intimately and very carefully, they said that, hey, these very complex heuristics and approximation algorithm or randomized algorithms for solving these problems, etc., might be great, but inherently I see a huge amount of interference that happens in some regions, and these graphs are so dense in terms of they are not sparse. So even if I deploy these kinds of algorithms on them, what good is it? Because eventually they cannot have a very good solution. They realize this is the issue. And so let's not go in that direction and waste time in trying to find a most beautiful solution when inherently it doesn't exist. The second thing they realize is that this is not really a graph which is cast in stone. What I meant by that is there is a good opportunity here for moving around the load stores, definitions, splitting live ranges, doing lots of transformations to this graph to simplify it. And that is the approach they chose instead, and reduce the denseness or the topology of the graph so that it will become colorable with even simple heuristics. The compilation time is of essence. A register allocator cannot keep running and running and running and running. And even if it did, because the graph was so dense, it had what are called as cliques, it was not colorable. So we'll look at these issues, look at the transformations approach which compilers adopted, and that led to great solutions and very reasonable compilation time. So that's a very creative use of changing the problem's definition. If this were a traveling salesperson problem where the cities cannot be moved, hopefully, then there would be, of course, room for solving it using better and better algorithms. And of course, assuming that the cities are also not a dense graph, they are sparse graphs. And by taking advantage of topology and randomization and approximation and whatnot, even the costs on the edges or whatever the problem's formulation is, there would be a different solution. So there is even both problems are in the theoretical sense NP complete. They're very different. So with that preface, let's look at this problem at hand. And in fact, not just this problem, but this principle has been followed through and through pretty much in every compiler backend problem, which happens to be reducible and is reducible to NP complete there by proof NP complete. But never ever a single algorithm is more than n square there, because there is no room for it. On the other hand, plenty of transformations, plenty of program changes, etc., have been attempted, which work in a very quick manner and change the underlying representation, make it less dense, much more sparse, much more simplified, and then solve the problem. That is at the heart of the solution strategy. So let's look at this S1, S2, S3, S4, and let's learn how this coloring problem really works. And in this particular case, the nodes must have different colors. And what we'll do is when it is completely sparse, it is colorable using just one color. Here, obviously, it is not colorable using one color. It has to have at least two colors because there is an interference. Then this one, it is still two colorable. You can see that we can alternate between the colors here. But the moment now we introduce another edge, you can see that from the previous one, we have just one couple of edges introduced here. The problem changes, and now you can see that this is not two colorable, but it must have three colors. The reason is you can see that there is a subgraph here which is called as a clique. What exactly is a clique? Clique is any subgraph which is completely connected. Any two nodes in that directly have an edge. So if that is the case, then K size clique must have at least K color. We have three size clique here. We must have three colors. If we take one more step and add one more edge, we'll see that it will become four colors are essential because it will then be a clique of size 4, where it's a subgraph of size in which any two nodes will be directly connected with each other. If that's the case, then all four have to have different colors, and clique of size K will have an essentially K colors. And so with 32 and 64 colors at hand, the question is how often do we get cliques of size 32 and 64? The answer is in large scale programs, very, very often. Because compilers do inlining, they do transformation, blah, blah, blah. And all these creates huge interference graphs, and therefore we will exceed the number of colors and there will be spill. No matter what algorithm we use. This is again not an issue of algorithm, as you can see. Any clique of size K has to have K colors minimum, regardless of any algorithm. So, so that's the empirical observation on which the compiler decided not to go in approximation, randomization, heuristics, blah, 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 many more things, theoretical results, etc. But said that, hey, these cliques and things are there. So let me try and simplify the underlying graph and break the clique, do something. And if I can, then I can do with less colors. If I cannot, there's no other choice except living with the K number of colors. And there are many, many transformations. We don't have time to get into all of them. But let's look at the core coloring problem. So here is how the heuristics for register allocation. There are two of them which are very famous and used in practice and implemented. One is called Ch1 and second is called Briggs. And we'll look at them and see how they try to do coloring. Now this particular coloring step is also called a simplification of the graph and trying to find out which of the nodes of the graph will always get color. So the observation is this: if the degree of a node, which is the number of edges which are there and that node, is less than n. What is n here? N is the number of registers. So if the degree is strictly less than n, you can see that this node can always be colored. Why is that claim? The claim is this, that let's in the worst case, all the neighbors get different colors. Okay, for a coloring, maybe they interfere with each other, etc., etc. And so they all have to have different colors. Even if you give all different colors to my neighbors, you still have a color left for me, where me means the current node, which has a degree less than n. That's the reasoning. So if that is the case, then the node can always be colored. and the algorithm tries to pick up all these nodes from the interference graph, remove them from the interference graph, and say that, hey, these are the nodes I don't need to worry about. And by doing so, if it is able to remove all the nodes, then the whole graph is colorable. Of course, that doesn't happen. And after removing all the nodes which are degrees less than n, we run into the case that all the remaining nodes have degrees greater than equal to n. So we reach this invariant. If we don't reach this invariant, we are done. That means we can give out simple colors, pick a node, give a color which is different than its neighbor, and keep doing that for all nodes, and we'll be done, and the whole graph will nicely fit in our registers, and we'll be very happy. But after removing each of these nodes which have degree less than n, what if we are left with degrees greater than equal to n, then we are at a dilemma. One possibility is this, that it may be still that we are able to color them with n colors. Why? Because consider again all my neighbors. They may not interfere with each other. And so some of them may share a color, even if my degree is greater than equal to n. I easily see this particular case that even under this situation, if two of my neighbors maybe share a color, two or more, then you could still have some color left for me, and so I'll be colorable. That will be case one. The other one is, no, not really. If they cannot share colors, and if they all must have different colors, then you have no color left for me. So this leads to either identification of a clique. You have to go into a case where they must have different colors. That means I must establish that they form a clique. Or if I am not ready to undertake that analysis of determining the clique, then I operate under certain assumption and find out if that assumption gives a good solution or not. And typically, we don't have time to find cliques in the graph. The reason is this, that to determine a clique, consider the number of edges inside the clique. It is always order n square. So the algorithm will spend tremendous amount of time in just determining if the clique, if it is there, it's there, you can't change it. So what's the point in finding it? This is not a theoretical exercise. So it will start making an assumption in a pessimistic or an optimistic way to treat this particular case of how to interpret degree greater than equal to n. So the optimistic assumption here is there is no clique. Okay. Some of my neighbors will share the colors. Definitely, they are all not interfering with each other, and they are not forming a clique. And then under that assumption, do something and order their coloring and then do the coloring. The other assumption is no, they will form a clique, and because of which carry out a spill right now. Take the least bills cost node, carry out a spill, simplify the graph, remove this node from the graph, and then keep moving. The first assumption was, the pessimistic assumption was because of Ch1, Gregor Ch1, who wrote the graph coloring allocator first. During those times, the number of registers were quite small. So this assumption was quite realistic, that the degree of the graph greater than n means very possible there is clique. Whereas as n grew, the number of registers grew, 32 and now 64. Whenever this invariant is met, it's quite likely that this is not, there is no clique of size 64, so to say. Maybe there is a clique of size 50, but still you would have this degree greater than equal to n true there, because of obviously it is not a part of clique, but it is still a degree, high degree node, which is interfering with a lot of stuff. you can easily construct a case where both possibilities are there, that there is a click and there is no click. And with large number of n, this assumption is less likely to be true, at least in many cases, than when n is small. So Ch1 made that assumption, Briggs made this assumption, and that led to two solutions. So I hope this sharing of colors and these possibilities of a click is a clear concept. If not, let me just quickly illustrate this, and then we'll come back again here. We'll go to the whiteboard and then illustrate it. So here is the concept. So this is me, which needs color, and here is my neighbors, which are to be colored. And I have met an invariant that this degree is greater than or equal to n. Okay. Now, one possibility is this, that look, maybe these two interfere and these two interfere, but this and this doesn't interfere. So this can get a green. This also can get a green. Now I have reused the color, and therefore fewer colors are used here. You can see only one is used, as against a case wherein all of them have some interference with each other, and these kinds of complex case in which much more are used. So this is the second one, when they're all interfering and is a part of clique, is if it is greater than or equal to n, no color is left. Because remember that the clique of size n plus 1 here, which is the case at least, and you will need n plus 1 color. So in this case, coloring has failed. But if that were not the case, such as there was no interference here, maybe no interference there, maybe no interference between these two, things like that. So all these kind of cases, this will also become green, that might become green as well, no interference. Fewer than n minus, if there are k nodes which don't have interference, there will be n minus k colors which will get used. That basically means for k greater than equal to 1, I will have a color. And so basically, in that case, when there is no clique, I'll be colorable. Now we don't know whether this is the clique is the case or the sparsity is the case. And the Ch1 made an assumption that this is Ch1's assumption, C, and Briggs made this assumption that there is no clique. And based on the values of k and the kind of codes that exist, obviously these assumptions were the common case during those times of when the algorithms were developed. And that's why both algorithms have the merit of their own. But of course, currently, optimism pays off, and this case is that there is no interference, and that was shown that empirically that happens to be the case many times. So with that, let's go back to this where we were, and then look at the okay, so this all right, so these were the two cases, implication that no clique, that is Ch1, and clique, which is Ch1, and no clique, which is Briggs. So how do these algorithms work? So Ch1 says that again the first step remains the same for both, but when you reach this invariant degree greater than or equal to n, Ch1 says that yes, there is a clique. Let me find the least spill cost node here and go ahead and spill it, which basically means consider it to be memory allocated, not register allocated. Remove it, and then again, so this is a graph simplification. So once this is spilled, remove all its interfering edges, remove the node from the graph, and that graph is again fed back to the step 1, and we'll keep doing this till the whole graph is colorable. So that's Ch1's algorithm. And in that process, you might go ahead and generate a lot of spill. We'll look at one example which is where Ch1 actually carries out a spill when it should not. It's a sparse graph, of course. And the Briggs optimistic coloring algorithm is what is implemented these days in all GCC, LLVM, all kinds of different compiler infrastructures with a lot more complications added to it. So what does it do? Again, the first step is the same, degree less than 1, n, keep simplifying, removing, because it's guaranteed a color. And now when we reach this invariant degree greater than or equal to n, here is where we optimistically do something. So we actually don't carry out a spill decision right now, but we remove that node and we keep pushing it on a stack. By the way, in the first step also, the difference between Ch1 and Briggs is this, that Ch1 is not doing the coloring decisions immediately. So he is removing all these degree less than n nodes, pushing them on the stack. So the stack at the bottom, you'll see that the nodes which are guaranteed to get color, they are at the bottom of the stack. On top of them will be all these nodes which are degree greater than or equal to n, but which have least spill cost first, then the higher spill cost, and so on. So the stack will get organized from guarantee of coloring nodes, degree less than n at the bottom. On top of them will be nodes with lesser spill cost, and the spill cost will keep rising as we go towards the top of the stack. So therefore we'll just sort in some ways the graph into the stack. That's what is going on. And when all the nodes are removed, we start coloring. So here is what Ch1 will, Briggs will do. Pop the node from the stack, and it is from the top, so it will have the highest spill cost. As I was telling you earlier, in the second step, the stack will be ordered from the bottom to the top with spill cost increasing. And at the top, therefore, we'll have the node with the top highest spill cost will take in the first, that will be the first one to get a color. And during coloring, so we are now doing coloring, popping these nodes, giving it a color. We will make sure that, of course, the colors are different, obeying the constant of interference. And if we do not have a clique, we'll get away with giving color to everybody, and we'll not have a spill. However, it may not be the case if we were in a real spill situation, because finally we are just optimistic, we have no guarantees. And if we don't during this particular step, then what do we do? So then we carry out a spill. We spill this node, and now the structure of the whole graph has changed because of this reason, that we have actually discovered a clique, we have discovered a node which needs to be spilled here and which should be removed and so on. And we did all that, and we remove that node from the graph, and then we again give the graph back one. We restart the whole thing. We do not keep going because it's a different graph, and these heuristics, there is no monotone, etc. on the quality of solution. So once you remove a graph, when you remove a node, you must start from scratch again from step one, and that's what they do. So some of these examples I will probably pretty much what is going on here. They're building this into the stack, and then they're trying to give coloring, and in some cases we are able to give colors, in some others we are not able to give colors. That's pretty much what this just illustrated. Here you can see that, let's just quickly look at it, maybe. So here is an interference graph, n is equal to 3, and we start with degree less than n, which is degree 2, and we put that into the thing. Now we can see that after we remove it, the degrees of the remaining nodes, some of them are 3, some of them are 2. So we could take either S2 or S3, and that we put S2 here. Again, we remove that node, remove its edges, and see if the degrees are less than n here. We are still in the step 1 here. So you can see now that we can give S1, S0, or S3, any of them, and we pick one, let's say S1. Again, we remove the node and whatever the edges which are incident on S1, and then we have degree 1, S0, or S3, so we can pick this. So we never in this particular example reach step 2, okay, and because of this ordering, we sorted the thing, and this is colorable because we are still in the step 1, and so once we start popping, that's what we should get, and we start giving, and this is how we are able to do it with 3 colors. So there are examples in which, of course, you can be pessimistic, you can be optimistic, but you really are in luck, and you don't have any spill. And then there is a case, of course, you are actually in a spill situation because you ignored a click and you got to throw that node away and restart from step 1. So I won't get into that. Here is an example of a simple example of where in and we'll do this and kind of do little concluding remarks for this register allocation. Then we'll take up the review and that paper next time. So this is a classic diamond graph in which degree is 2. Each one is degrees 2. Of each node is degrees 2, and n is equal to 2, right? So we are right there in the second case, or the invariant. Now the question is, how do we interpret this? As per Ch1, spill. As per Briggs, optimism. So Briggs will take the whatever is, we'll just do a random order here. 1, 2, 4, 3, something. Least spill cost node, and we'll push it onto the stack. It will take these 2 here. Let's say this is the least spill cost. I'm randomly picking one. And then once it simplifies that, the degrees of the other ones have fallen below once, and then it will take maybe 1, and it will take 4, and then it will 3, something like that. It will put, and now it will start coloring. So it's been optimistic. It didn't carry out any spill, and it will try to do and see if we can do it with 2 colors. So let's say this one was 3 was colored first, so that was given red. 4 was colored next, that was colored blue. Okay, and then we had to color 2. So obviously we can't give blue, so we tried giving red, and that worked. And then, oh sorry, this was 1, so this one would be blue. This is 1 here, and that one was 2, so this one would be blue. Oh, sorry. So let's do it again. First is 3, that is red. 4, blue. Blue. Number 2, red. Because it will have to be different, and it will try to do it with a color. So you can see that this is 2 colorable, and the optimism paid off because obviously there's no click here. And this shows that when the graph is sparse relative to n, optimism paid off, and you can color it using n number of colors. And this is where the Ch1 would have carried out a spill, which is really unessential. So this is an example which is used to illustrate the superiority of Briggs over Ch1, especially with regard to sparsity with regard to n. A simple example. So the last thing in this register allocation business is I mentioned to you that the approach has been taken, which is um, not one of deploying very expensive algorithms and relying on theory, etc., to simplify, because the key observation was we are going to have a clique, so what's the point? Maybe we should do something to break the clique rather than trying to deploy these algorithms which will eventually come back and say, hey, too bad, I can't do anything. So one key observation is this, that many live ranges are what we call as amenable to certain transformations, and we will use those to our advantage. So here is a simple case of this, which is a very classic example. If you really look at it in terms of spill costs here, there is a definition of X. Nothing happens to X for a very long time, including there is no use in that loop which you see there. But there is a use of X downhill. And in terms of Y, however, this range is not only live through this loop, both ranges are live, by the way, through the loop, but it also has active uses and definitions inside the loop. So the spill cost for Y is higher. Now, if you go for a solution which is if you look for a solution which interferes X and Y, since the excess spill cost is less, it will go ahead and spill it and give the register to Y, which is doing the right thing. But that's not the only thing one can do. One can easily go in this particular way. We can try and split the web and get rid of some of the interference and make it colorable. So in this case, here is another example in which we again have some definitions and uses of Z now, which are outside of the loop, but X and Y have the uses and definitions inside the loop. So what we can do is we can split the live range of C out on the loop. And here was the original interference graph, the clique of size 3, and we can't color it with only 2 registers. But if we do the splitting of the Z at the boundaries, we will be able to do the coloring with some little extra load stores as the boundary load stores. So this is not colorable because Z, X, and Y both, they all interfere and it's a clique. So we might have to carry out a spill here, which will be the Z split, which will be the Z, which will be spilled. But here is a split. So what we did was there was no use of Z. So we cut the live range into 2 pieces. One is top and one is bottom. So around the loop, we split it. And now what we can do is the interference graph looks like this is a Z1, the first one, and the second one is a Z2. And there is an interference between X and Y, and there is no other interference. Now you can see that this is too colorable because one can give register to X and Y, and the same register can be used where there is no interference with Z. One of the registers of X and Y can be used for Z. And so here in this case we use Y's register, and that's why it become too colorable. Now obviously you can see that after the first use of Z we'll have to put a store, and before the second use of Z we'll have to put a load, and those will be the cost for us, and that's how we can save spills. And if there are enough uses and definitions which are covered by these boundary load stores, we'll be good because they're anyway sitting outside the loop. So we get rid of, we give R1 that register, then we do a store on it, we remove, we save Z in the stack, and then we use R1 for Y, and then once we are done with the loop, we restore Z from the stack into R1 and use it, and that's how this solution works. So splitting helps, that transforms the graph and helps us to avoid spills. So this is the store and this is the load that we have inserted, and that will take care of this solution. So obviously how to split, where to split, how are the boundary load store, their cost, whether they cover the other pieces of uses, those are all questions, and they are to be answered. Typically that's done around the loops. That's a topic by itself, and it does depend on the boundary load store, the shapes of the live ranges, many factors. But this is the simplification of the graph it leads to, and that's the better approach than doing any heavy duty algorithm. And you can see that the reason it became better is mainly because it removed all this interference and made it colorable. From a click, this was a click that we had in the original program, and after doing splitting, you can see that it led to this simple graph, and that led to with a simple algorithm, but the transformation of underlying interference graph, it led to a better solution. All right, so that's all today. Sorry to go a little over. Thanks for bearing. And if you have any questions, I'll see you in the office hours. So we'll stop here, and the next time we'll do a review. And I will also introduce pretty quickly the machine-dependent optimization, which leverages the register allocation in the next lecture. As such, we won't have that topic for the exam, the leveraging of machine-dependent optimization, but it's nevertheless a very important area in which still a lot of work is going on. So we should really study it a little bit. See you. Thank you. Bye-bye.